I'm going to talk about optimization guidance strategies for UAVs with some application for target tracking of ground and marine vehicles. So as Pedro said, I was here as a postdoc researcher from August to September, more than 2 years, okay. Okay, I'm going to skip this. Oops, doesn't work. Okay, what are the motivation of doing optimization? So there are several reasons. For example, if you think about the automotive industry, you are interested in in computing lap time trajectories in order to give some insights to the real driver. So where it has to brake, accelerate, to what kind of point you have to reach in a given turn. If there are just one, it's called apex point or two apex points and so on. And or if you have UAVs, you are performing some long endurance missions, you want to understand how to exploit the wind in order to perform some efficient trajectory. And or if you have you are doing some cooperative motion planning, you want to understand what kind of trajectory we want to perform in order to be in formation, right? So the goal is to develop an optimization framework for motion planning for in this case UAVs in dynamic environments. So we want to take into account wind features or other feature of the environment. So just to so this is a motion control system architecture. So what I'm going to focus is on the trajectory generator. So the trajectory generator is going to give us a reference trajectory or desired trajectory for the controller. Why we want to do this? Okay, if you compute a trajectory that satisfies the dynamics of your system, then you see that the performance of your vehicle, of your UAV or race car is going to increase it. Okay, so this is actually the motivation of my PhD. So I started playing around with the race car, and I was using a tool called ADAMS, and I saw that it was implemented some just simple PID controller, and the vehicle with virtual driver was able to track a path, so the center line of the track, but it was really, really stiff. Like it was, accelerating, brake. I was able to see some oscillation of the suspension, but if you really compute a trajectory of your system, it satisfies the dynamics, you can see that the vehicle is more comfortable with the dynamics of itself, okay? So you can increase the performance of your system. So this is the motivation. We are going to focus on this tool. So the tool that I'm going to talk about is the Pronto toolkit developed by John Hauser, who's using it from more than 10 years more. So the idea is the following. We have an internal vehicle model which describes the vehicle that you want to understand, to explore. And then you consider a feedback controller, which is actually not a controller that you are going to design, but it's this gives us some robustness in order to explore the trajectory of your system. So it's nothing, it doesn't take into account human behavior or something like that. So now we have a feedback control system. It generates, so given a curve, it generates a trajectory. So now we can evaluate our cost function that can be least square cost function to normal, or we want to minimize the time. We have the current cost. What we can do is to perform some optimization steps. So we look for a decent direction in order to decrease the cost function. And then what we can do is like backtracking and search. So how far we have to go in order to decrease the cost function. Here we have a curve. It does not satisfy the dynamics of our system. What we can do is now to project the curve into the manifold of our vehicle. Oh, okay, so this is actually the main idea of Pronto Toolkit. So what are the advantages of this approach? So at each iteration, we have a feasible trajectory. So it satisfies the dynamics of our system. It can handle some non-trivial constraints. We will see later what kind of constraints we can consider. We have some robustness due to the feedback controller here. And we have reduced from my experience, we have reduced the computation time even for complex dynamics. So the first step, I added this slide because I was talking with some of you regarding the projects. So an important step is the dynamics of your system. If you are exploring or you want to compute trajectory of a quadrotor or fixed wing, you don't have actually to consider a very complex UAV model, right? Because, I mean, you can do it, but do you really need it? I don't know, probably not. If you are, for example, if you're computing minimum time trajectories, what is really important, for example, is the load transfer. Maybe you cannot, you can neglect the suspension system, but even you have some dynamic features captured by the model. So this is an important step. So you have to choose the model of your system. Then, given a model, you start thinking about what kind of trajectory we can do it. So for UAV, so it's like analysis of equilibrium. So for UAV, you are studying the trim trajectories. And then you apply some optimal control-based strategies in order to explore the system. And what we have proposed is to have so it's called a virtual target approach in order to enforce a trajectory tracking or a path following behavior. And given that the trajectory of our system, we can do some, we can analyze vehicle maneuverability and capabilities. So that probably you can get some insights on what you can change, what kind of parameter of your system you can change in order to increase the performance. The main challenge is that since we have nonlinear dynamics, nonlinear constraints, in order to generate this kind of trajectories, it's challenging. Yeah. You have to choose how you initialize the algorithm, what kind of constraints you have to include in your system in order to get nice behavior and so on. So this is just some slides about the model I'm going to use in this talk. So this is the coordinated flight vehicle. You can check this model, the implementation also the Randall's book. And so it's just a single planar rigid body. We are enforcing coordinated turns. So we have an equilibrium between the centripetal forces and the gravity. And so we have some state and input constraints. These are the equations of motion. And it's a pretty simple model, but captures some interesting dynamic feature of your UAV. Then we consider also some constraints. So in order to avoid stall, you consider a minimum airspeed for your vehicle and so on. Then what we can do, okay, if we are interested in exploiting the wind in order to increase the performance of our UAV, in order to save energy, we can include in our model the wind and ask what kind of trajectory we can do in order to increase the efficiency. So we can include some aerodynamic features like the drag, and this is the model. Okay, so we are including here the wind. We have airspeed, ground speed, and so on. But we can discuss later about this implementation detail.
So here the input is what?
So yeah, good question. So the input here is the thrust, T, and the roll rate, the roll angle. Okay. And here we are assuming that the wind is time invariant, okay? Maybe space varying, but time invariant. So then we can increase the complexity. We can go to the 3D UAV model. For example, if we want to understand what is the best trajectory of our UAV in order to land on, for example, UGV, a ground vehicle, for some reasons. And so you have to include some, the vertical components of your UAV model. This is a 3D point mass model. You have some simplified aerodynamics for the drag and lift. And here, the control inputs are the thrust, the roll rate, and you can assume to control the lift coefficient. So it's, if the angle of attack is small, okay, you can assume to control this coefficient. Then we have some state input constraints, another constraint on the airspeed, on the load factor of your UAV, roll angle, and all the inputs. So it starts to be complex, to be like a very complex UAV model. Actually, the Pronto toolkit is going to work for a general class of constrained vehicles. The important thing is that since Pronto is based on, it's a base Newton method, so it means that a given trajectory, you're looking for a descent direction in order to decrease the cost function. It is based on the derivatives of your dynamics. So what we need is that the dynamics of your system is, you can compute at least the derivatives of your dynamics, or your F, okay? So what kind of constraints we can include? Well, as I saw the previous model, we can have like the roll angle bounded by a maximum roll angle, right? Maximum value. And actually, this is something not so smooth. So how can we include the constraint in our framework? So we can have some smooth function which enforces the constraints. So this is a quadratic cost function. We want to have that the constraint C of, in this case, the airspeed is less or equal than 0, so something negative. And this is a smooth function that we can include in our framework. So, okay, we have a families of vehicle model. What we can do? Okay, we can start studying, analyzing the trajectory of our system. The first step is that the so-called trim trajectories. So we assume that the acceleration are 0, part of the acceleration are 0, and we study the trajectory of the system that can be performed by using appropriate constant inputs. So for just to give you an example, for the 3D UAV model without wind, we have that derivative with respect of time of the airspeed is equal to 0, so it means that the airspeed is constant, and we have a constant turn ratio. We have this nonlinear equation in 3 unknowns. And what we can do is try to solve these nonlinear equations, okay? Even for very complex aerodynamic features here. What we can do is, this. Okay. So what we can do is to use prediction corrector continuation method. So we start with a very simple trim trajectory, for example, going straight. So 0, for example, in this case, 0 lateral acceleration. We can do a prediction of what is if we increase the lateral acceleration of our vehicle, we can do a prediction. And then we project in the manifold, our equilibrium manifold. So we compute another trim trajectory. And even if we have some complex aerodynamic equation, we are able to compute some interesting trim trajectories. For example, in this case, something happened. We are not able to compute a new trim condition. We change a little bit the direction where we look for it, okay? So in other words, we decrease the lateral acceleration instead of increasing it. And we are able to compute new trim conditions in the range of the of the aerodynamic features of our model. And these are some trim trajectories of the 3D point mass model, which is increasing the altitude. This is the loiter, and this is the helicoidal maneuver of the UAV. Okay, what we can do now that we know what is the range of our system, we know some trajectories. What we can do is that given and desired curve, so we want to perform like a loiter maneuver, we can set up an optimal control problem. So we can ask to, okay, look for the couple XU of our system, so the state input, such that we can minimize this cost functional, subject to the dynamic constraints. So the XU has to the couple XU has to satisfy the dynamic constraints, and more some state input constraints. Here we have some matrices, Q and R, which in some sense affect the exploration strategy of, the exploration strategy. We'll see. So this is the pronto. How does it, just the big picture of how does it work. So we have the trajectory manifold of our system. It can be something very complex. We can start from a trajectory C of our system, so it satisfies the dynamics of our system. We compute some kind of approximation of our system, so this linear approximation of the manifold, so this plane. What we can do now is to look for a descent direction, so we want to minimize the cost functional. So you see here, we look for a ZI curve, okay, minimize the cost function. Then we do a line search. We look for a gamma such that in that direction, we decrease the cost functional. And then what we get, Ci plus gamma zeta I, does not satisfy the dynamics of our system. So what we can do is to project. So using this idea of projection operator. Given a curve, we project and we satisfy the manifold of our system. So it's an update step. And it's interesting because when you are close to a well-defined minimum, you get a nice quadratic convergence to the optimal point, or to the optimal trajectory. Okay, so these are some trajectory exploration based on a desired curve, some experimental test developed performed by the LSTS. So this is the X8 vehicle. So what we've done here is just to take some experimental data. So it's like a model validation. Take the experimental data, set the desired curve as desired curve to experimental data, and look for the trajectory of our system such that is as close as possible to the experimental data. And actually this was I think the 2D model. We have a nice matching between our UAV model and the experimental data. You see, this is the roll angle, I think, yes. So now what we can do with our model, with this tool, we can perform some exploration strategy. So we look for some trajectory that minimize some cost functional in order to perform some missions for our UAV. So here we use this virtual target vehicle approach in order to have some path following behavior. So the goal is to drive the vehicle to reach and follow a given path with probably a desired speed along the path. So we can define, so in this case it's like a loiter maneuver, okay? We can define the virtual vehicle here, the blue box here, and we can describe the position of our actual vehicle with respect to the position of our virtual vehicle. And, okay. So this is what I was saying. You can describe the position of our UAV with respect to the position of the virtual vehicle, which is parameterized with respect to the space. So it's not a trajectory tracking, but it's more path following. And what we can do is here that we can model our system by taking into account the error between our UAV and the virtual vehicle. Actually, in doing this, we are including in our model this U3, which is the velocity of the virtual vehicle along the path, the desired path. So in some sense, we are controlling the position of the virtual vehicle along the desired path. And yeah, this approach actually it was interesting because at the beginning, because using the transverse coordinates, which is just a projection of the position of your UAV with respect to the desired path, you cannot go far away from the desired path. You have some constraints on the lateral displacement. With this approach, with the virtual target vehicle approach, you don't have this singularity. Okay, it's EY doesn't appear in the error dynamics of our system. Okay, so now given, okay, this was for the 2D model. We can do something similar for the 3D model using a reference frame. So our UAV is here. We define a reference frame along the desired path. We can describe the motion of our UAV with respect to error between the UAV and the virtual vehicle. And well, there are some, I'm going to skip this. It's the same main idea of the 2D model. Even here we have some, we are avoiding some singularity of the transverse coordinates. And what we can do now, okay, we can set an optimal control problem. So given a maneuver, like a loiter or something else, we look for a trajectory of our system XU, which is close as possible to the desired maneuver. The XU has to satisfy the dynamic constraints and some state input constraints. Here, this is some numerical computations. No, why it doesn't work. Okay, so simple one. We want to, so we have an initial condition for our UAV, and we want to follow a desired path with a given velocity attached to the path. So the blue box is the virtual vehicle. So what we can see here is that, okay, at the beginning, the UAV, there is the speed here, it's weird. Okay, the velocity decreases in order to turn, okay. Here, the UAV is able to have smooth transition between the initial condition and the straight line path. The UAV reaches the maximum roll rate here, so it's something very, let's say, aggressive for the roll angle and smooth for the airspeed. Actually, I want to show you here how does it work the Pronto with this simple case. Okay, let's see. Okay. So this is just the dynamics of our system. So it depends. So depends of the position of the virtual vehicle. And then, as I said before, we need to compute some derivatives of our system in order to look for a descent direction. Okay, so run this simulation. So at each step, what we are doing is that we start with an initial trajectory, which is this green line here, which is just a straight path. It's very simple to compute. It's a trim condition. We have to solve just some nonlinear equation. We start with this trajectory, and we want to compute the best trajectory of our UAV such that we follow this straight line path. Okay. We start also with the constant airspeed, which is 90 meters per second. And then we are able to, with this projection operator, we are able to evaluate the cost function. we look for a distant direction with this ZV. Then we do some line search here. So we compute the gamma such that we decrease the cost function, and then we update our trajectory here. And in this iterative process, we see actually that after a while, we get some nice trajectory. Let's see. Yeah, it looks like the second order is working right now, so we should go faster now. Yeah. So what happened here is that we found a local minimum of our system with high precision. And yeah, these are the trajectories of our UAV at each step. So at each step, this is important. Each step, we compute a trajectory. So actually, we can perform this trajectory for our UAV. Okay. Yeah. So. Let me see. We can include it. I don't know if there is roll rate here. So U3, that's not U3, U2, let's see. I don't think this is implemented here, but yeah, you can do it. EXA, yeah. Yeah. No, that's, thanks. Yeah, thanks for this question, it's important. So the theory behind this tool is that we are dealing with an infinite dimensional system, okay? So there is not discretization, there are not polynomial parameterization here. So we are dealing exactly with the system, with the differential equation of our system, okay? Numerical, okay, then you have to discretize when you compute the trajectory, but the theory behind that, there are not parameterization. It can be, or can be something unfeasible. So you look.
It could be infeasible.
Yeah.
So you basically solve it.
Yeah, exactly. Yeah. And this is important because in this iterative process, every time you have a trajectory, so that you just can stop the simulation. Okay, this is the trajectory. I can give this trajectory as a reference for the real UAV. What?
The reference trajectory is the one you want to get to, long term, just a series of
It can be something unfeasible, so in that case, it's like parameterization with respect to space. So given a path, so a loiter maneuver, you can describe it using the arc length, right? So you fix the curvature of your path, and then you simply integrate it. So, yeah.
So is it the solution of the differential equation?
So it's x prime equal to cosine of the angle. Yeah. And the angle is given by a simple integration of the curvature for the.
I was just wondering if you have a trajectory given as a series of wavelengths.
No, it's yeah, in only time. Yeah. A loiter or something more complex, I'll show you. Yeah. Yeah, exactly. And actually so this is just the first step. And then what we can do is, since we have some state input constraints here, in order to include the constraints in the optimization process, you are using some barrier functional let's say, trick. So you're including the constraints in the cost functional. And this, let's see, dB count. Okay, so when we found a minimum, we update the parameters of our let's say, barrier functional. And we run it again. And what we can see, we use as initial trajectory the optimal trajectory at the previous step. So this is the iterative process. It's like a continuation method, okay? And what we can see here now, at least I hope so, there should be the roll angle somewhere. Yeah, it's going to approach, the roll angle is going to approach the boundary. So at the end, the vehicle is exploiting the maximum turning rate for its capability, okay? We got another minimum. Let's see the roll angle. Yeah, it's almost at the boundary. And then we can update again our parameters, use the optimal trajectory as a new initial trajectory, and iterate in this iterative way. Yeah. So I'm going to stop this now.
So just
Yeah.
so the green, so at the end, what you
At the end, okay. At the end, we get the optimal trajectory of our UAV model. Okay, so the green line, and actually the position of our virtual vehicle, the blue box here, along the desired path. Okay.
satisfies the dynamics of the vehicle and the constraints and all.
Exactly. So yeah, you see, this is the roll angle. It satisfies the constraints, and probably also there are some constraints here for the airspeed, for the thrust, and so on. Oh. This is another simulation. Okay, this is another interesting stuff. Oops. So here in this virtual target vehicle approach, you can initialize the position of the virtual vehicle along the desired path, okay? You can choose it. But then in the optimal control framework, you have some matrices that is going to affect the exploration. So here what I'm going to show you is that even if the virtual vehicle started here, since you want to minimize the error, the longitudinal error and the lateral error between the actual vehicle and the virtual one, the virtual vehicle is, had this kind of motion going back, try to minimize the lateral error, and then wait a little bit to waiting the UAV approaching the desired path and then going together. So you see, this is the velocity of the virtual vehicle. So it's a virtual vehicle. We don't have constraints over there. So it has a very high and negative speed. So it means that it started here, going back, waiting for the UAV, and then go on. Yeah, Pri.
So here, I'm assuming the entire trajectory optimization step is offline.
Yeah, this is offline. I show you the.
Given your optimal trajectory for the states and the control input, you have some kind of controller which actually ensures that the UAV follows.
Exactly.
So what would be the difference between this method and non-linear FPC, for example, if you choose to execute this trajectory optimization at every time step, right?
Okay, that's a good question. Okay, so for nonlinear MPC, you have like a control horizon, prediction horizon, and control horizon, right? So in some sense, when you fix that horizon, you are discretizing the space of your maneuver. Okay, in this case, you are not doing it. So it's like, okay, I'm looking for the best trajectory of our system. I don't care if, let's see. For example, if you are doing some very aggressive maneuver, if you choose a horizon which is not so good, you can have some issues over there because you are dealing with an unstable system. Probably you are going fast with your UAV. you don't see what's going to happen later if you choose, for example, if you have some numeric, computational load of the MPC, so you don't choose a long horizon, no, okay. Then you change the window, okay, and what you can get, probably you are not able to compute a new trajectory. It can happen. In this case, okay, it's offline. You compute the entire maneuver, the entire trajectory, but yeah, you get a nice. No, it's the entire maneuver, the entire, yeah. Actually, you can do some, yeah, you can do, of course, like an MPC approach based on this technique, this approach, yeah. And these are the loiter. So here, the UAV is, the heading of the UAV is, the direction is the opposite to the loiter. So what's going on here is that the virtual vehicle is just with zero velocity, waiting for the UAV going around and approaching the loiter. You see, at the beginning, the velocity of the virtual vehicle is almost zero. And changing some parameter of your cost function, what you can get is that a path following behavior. So we don't care to be in a specific point of your loiter at a given time. We don't care about it. But if we want to have like a trajectory tracking approach, we change just one parameter of our framework, that is the R matrix in the optimal control problem. And in other words, you are asking here to be in a specific point of your loiter maneuver at that time. So the virtual vehicle is not waiting for the actual vehicle to approach the loiter, okay? So in this case, your UAV is going faster in order to reach the loiter, a position on the loiter at a given time. And this is an interesting feature of this virtual target vehicle approach. Just one parameter, you can enforce trajectory tracking or path following behavior. This is a more complex simulation, so it's a mix between a straight line path and some part of the loiter. Okay. These constraints, these green lines, are based on the transverse coordinates approach. So if you don't use the virtual target vehicle, you have some singularity in this point because you are going too far from the center line of the track, okay? And here it's interesting to see that when there is a turn, when there is a turn, the right turn and the left turn, the virtual vehicle is going fast in order to. So the green one is the actual vehicle, our UAV model, and the blue box is the virtual vehicle. You can see this yellow line is the lateral error, and then here you can see also another line, yeah, this one, which is the longitudinal error between the UAV and the virtual vehicle. And here you see that the roll angle is something constrained at the beginning because you want to approach the desired path and so on. The green line is the gray. There is something that is not in the computation here. Just to give you, so you can do something similar by using this called transverse coordinates, which is different for the virtual vehicle approach. But in that case, you have some singularities, so you cannot go far. The lateral error is bounded. You cannot do something else, and it means that. Let's see. In this case, I'm going to stop this video just here. By using transverse coordinates, you have a singularity in this case. You cannot go outside this kind of, let's say, tube, okay? but with this virtual target approach, you can actually compute this trajectory without singularities. Everything is fine. You are able to compute a trajectory satisfying the dynamics of your system. Yeah, so this gray line are just a different approach to have a path following behavior.
Why is that singularity there? Because of the radius of the vector?
Because when you do, so for the transverse coordinate, what you are doing is that a projection of the position of your V with respect to the desired path. Okay. Here you can have multiple points. So you can stay here or you can stay here. It's not easy. Or here or here.
So if it were closer to the path, then there would not.
Yeah, exactly. Of course. Go. Good. Sorry.
Not with my question, but visual target, visual vector. How are you prioritizing these curves, like doublings, backs, or?
Okay, it's just like.
Because you need to like build a differential equation for that.
Yeah,
For the virtual target, and now you are making turns. And
exactly.
so
Yeah.
on. So
How can I do it? So the first part is just a straight line, right?
Yeah.
So it means that, so this is a planar model, so you have zero curvature. Okay, so if you think about the space parameterization, you have that the curvature is zero, so the heading angle is, let's say, chi prime, the derivative of chi with respect to space is equal to the curvature, so you are integrating something which is zero, okay? So chi is constant, and then you have x prime equal to cosine of the heading angle, and y prime equal to the sine of the heading angle. So you integrate it. But then at a given time, you have this term, you are changing the curvature, so you fix the curvature, like 10 meters. You integrate the heading angle, and once that you have the heading angle, you integrate the x, y position. So it's pretty a simple integration.
Okay, but then you, as you are minimizing for the whole trajectory,
Yep.
you need to have
You need to have the entire.
the whole
Yeah.
entire path.
Yeah, exactly. I can show you later. We can discuss about it. Yeah.
So in this case, it's always the terms of always constant radius you can't have.
It's not actually more or less constant. Okay, you have a smooth transition because when you want to compute the derivatives of you're looking for a descent direction. You don't want to have like kind of, yeah, exactly.
And but in this case, the trajectory is actually not feasible, right?
No, the blue line is not feasible for the UAV. So this is the point. We are looking for a feasible trajectory of our UAV, which minimizes the distance between the trajectory and the desired path, with a desired velocity along the path. Okay. Okay, these are some other simulations. I'm going to skip this because I think it's late. So this is a loiter maneuver with with constant wind. So here you can see a path following approach, and this is a trajectory tracking approach. And if you want to see some loiter maneuver and you want to minimize, in this case, the energy, you see some features of the trajectory. So here the UAV is exploiting the wind in order to minimize the energy. And then we have a moving path following approach. It's something related to, actually, it's the same idea of the presentation of Praveen. And so what we have done here is to embed the moving path following approach into the optimization framework. Okay, so this is the planar UAV model with wind. Okay, so with planar UAV model, so I'm going to skip this. So given a UAV model, what we can do is that we can use the UAV, there is another project about this, we can use the UAV as a relay, right? So the UAV communicates with the vessel or whatever, and then transmit the communication with the ground station, okay? So here you can have some other constraints, more or less complicated, which is you cannot go outside the given region. This is the, let's say, communication constraints. You can use some protocol, but there's some feasible hardware constraint. Then the UAV trajectory depends on the marine vehicles. So we assume to have this motion of our ASV. Simple enough. And then we can describe the motion of our UAV with respect a virtual target vehicle, which is the blue box here, which depends on the motion of our ASV, of our marine vehicles, which is this red one. We can describe the dynamics in this error. We can describe our model in this error dynamics. Okay, and this is the motivation scenario. Okay. So here the UAV has to loiter, since we have different speed, right? For the UAV, fixed wing UAV and the marine vehicle, we have to loiter with respect to the position of the marine vehicle. And this some computation with space varying wind. So at each position, the UAV is adapting the airspeed in order to compensate the wind, which is pretty interesting. What we can do more? So fixed wing UAV has limited fuel capacity, okay? So if we think about a scenario in surveillance mission in which we have multiple UAV, what has to do the UAV is to, after a while, has to go back to the base station, charge, and so on. So one solution can be to use a UGV, okay, that can be employed for refueling. So here we need some rendezvous strategy between the UAV and the UGV. So let's think about it, what we can do here. So we have the 3D point mass model. So in this case, we need the altitude of our UAV with some aerodynamic features, drag, lift, and so on here. And we have some control inputs which are the thrust, the lift coefficient, and the roll rate. Then we have the dynamics of our UGV, the ground vehicle, which is a 2-point mass model with a fixed path, as shown in the previous plot. We have some control input, so the UGV can move along the fixed path, so we can control the acceleration. And then we have some state input constraints, so something like the so-called ellipsion friction constraints of our UGV. So again, we can describe the motion of our fixed wing UAV with respect to the UGV, the ground vehicle. And we can, in order to have some successful rendezvous, we can impose some constraints on our system. So the altitude has to be less than 0, less or equal to 0. And we have some physical docking. So we want to approach the UGV in a given direction, okay? So if we are far away from the UGV, so we have a high longitudinal, lateral, and altitude error, we don't care about this constraint. But when we approach it, we want to be aligned with respect to UGV. So we embed this constraint in the optimal control framework. What more? So this is the optimal control problem that we want to address. We set a decided trajectory, so the error of our system has to be 0. We want to approach the UGV. And here some remark about the Q and R matrices. So tuning these matrices, we can have some, we are able to compute some aggressive trajectory or some smooth one, okay? And these are some simulation. So this is, I think, an aggressive, okay, it's an aggressive trajectory. As you can see here, the airspeed of our UAV is at the boundary, okay? And we, when we approach the UGV, we have something very close to the minimum airspeed. So we are approaching in a smooth way. And if we change a parameter of our cost function, we get a soft trajectory. So the airspeed is not bounded. We are not going very fast in order to approach the UGV. It's going very slowly. Yeah. That's all. Actually, we implemented a strategy to have just, we defined the aggressiveness index of our optimal control framework based on the trim trajectories, the trim condition, which are something important because you can set some, you can capture some features of your dynamics. And with this aggressiveness index, we are able to have a prediction of the rendezvous time when it happens. So the human operator can see when, for example, in this case, in 130 seconds, we are going to have this rendezvous. And these are the trajectories for different aggressiveness index, which is something smooth, but what I want to show you now is that, so this is the altitude. Green line is the actual trajectory of our 3D point mass model. And when we have some very aggressive, we are tuning our parameter, just one parameter, and we are saying, okay, I want to have an aggressive trajectory. We see that the UAV is going very fast, it's decreasing the altitude, and when it is approaching the UGV, it has this behavior. So it increases the elevons, so that it increases as well the angle of speed, angle of attack. The angle of attack is going to decrease the velocity. The altitude slightly changed here, and then you approach smoothly to the position of the UGV. And these are exactly what the steep glide and the flare of this landing maneuver. Okay, I'm going to skip this. I think it's time. Actually, this is the rendezvous on a 90-degree turn. So the UGV is bounded in a given track. So they have to rendezvous on, so in this case, you have some coupled longitudinal and lateral motion of the UAV and UGV. So the conclusion are that we set up some optimization framework for motion planning of UAV in dynamic environments. We are able to enforce trajectory tracking or path following behavior. So with this virtual vehicle approach, we are able to generate smooth UAV trajectories that can be used as a reference trajectory for the controller, the NPC or what else. Okay? And we developed a strategy to select the UAV trajectory with just one parameter of our optimal control framework. Okay. And yeah, that's all. Thank you. If you have questions.
Compared to the heuristic approaches like we adopt A-star for optimal trajectory generation, what about the real-time computational?
Now, as I said at the beginning, this is like, we don't care about real-time application. It's just offline computation, of course. But yeah, the point is that here we have, at each step, we have a trajectory. So it satisfies the dynamics. With A-star, you don't satisfy for sure the dynamics of your system. So it's, you need a, yeah, exactly.
Another point is about uncertainty of moving obstacles or environmental disturbance so how you tackle that one in your approach?
Yeah, we can handle obstacles here. So we want to avoid the obstacle, we can do it. We can handle also a moving obstacle, no problem for that. Regarding the uncertainty, well, in that case, I think we need a stochastic approach, okay? But I'm not sure how to handle it in this case, because this is a deterministic approach for computing optimal trajectory, so yeah. Yeah.
So let me give you a scenario.
Yeah.
Which happens kind of often. So imagine you have a certain wind speed, constant wind speed,
Yep.
and a UAV that cannot go as fast as the wind.
Okay.
And you want to do a straight line. So
Okay.
in the real world, the experienced RC pilots, what they do is that they go up and down and up and down and slowly straight line upwind. Do you think that it will compute a trajectory that will do this? What do you think?
Yeah, maybe, I don't know. We should try. But why the UAV is going down? Because when you decrease the altitude, the magnitude of the wind is...
When you go down, you take advantage of the gravity
Exactly.
energy. And
Okay.
you turn up and
Yeah.
just do
This recalls me there is a paper about the albatross model, something like that. Yeah. So yeah, probably you can look. We can run some simulation and get some interesting, nice behavior. Yeah.
because the reference is supposed to be a straight line.
Yeah,
It
yeah.
goes straight upwind. But would it generate a sawtooth motion?
Yeah, I think so. Yeah, why not?
Yeah, if you can put that in the model,
You need a straight
vehicles, probably
Yeah, I think so.
capture.
Yeah, good. Yeah.
Well, that was about the optimal control problem. So how do you select the terminal constraint?
Okay. Okay, for the straight line, you have some properties of the optimal control problem and so on. You have to set up that. So there is a matrix over there, which is P1. That's here. So for the straight line maneuver, you know that at the end of your trajectory, you are like in a trim condition. You are going straight with a fixed velocity, fixed airspeed, and so on. What you can do is that you can compute this P1. It's not something that we tune, but we compute the P1 solving an algebraic Riccati equation that gives you some properties and stabilize everything. So some nice property over there.
If you have the case of
A loiter maneuver. Okay,
you have a curved path that somehow it's random or
but curve path in the middle of the maneuver.
I mean, yeah.
We can always add a final path, which is a straight line, or a loiter maneuver that has some nice property. We compute this matrix, and
I was more talking about if you that as a C.
yeah, we can do it. Yeah, in that case, you have to tune that P1 matrix in an appropriate way. Yeah.
The other question was when you showed the landing
Yeah.
and that it increases kind of.
Yeah. Exactly.
Did you simulate stall properties there or?
No, there is. I mean, we just imposed some, the constraint on the airspeed. This. No. CL. Yes, we have a constraint on CL, so it's something.
Well, but that could go wrong because the CL decreases.
No, but we are assuming that we are in the linear region over there.
Okay, so you have
Yeah, so. And actually, I don't have here the slide, but we did a comparison with the complex model of the, with some nonlinear aerodynamic features in the paper, so I can send you. Kind of constant, because the position is changing, actually.
Okay, position
Yeah.
changes based on the configuration.
Exactly, yeah.
You just fix something and you see the.
Exactly, yeah.
So you use them, so the main use is for the segmentation of the before the optimization problem.
Yeah, it depends. I mean, you can use it like, let me see. Okay, let's see this. No, you have to initialize the algorithm with the feasible initial trajectory. So, yeah, at the beginning there was the big picture. You have a trajectory that satisfies the dynamics, okay? Because in that case, you have to linearize the dynamics. You look for a descent direction. So if you linearize with respect to something else, which does not satisfy the dynamics, you can get some. Maybe say you are close to the manifold, then you can project it. And regarding the trim trajectories, yeah, in this case, the desired curve is based on the trim trajectory. The desired curve. So we want to minimize the distance between the trajectory and the desired curve. So the desired curve is based on the trim trajectory. Exactly. Yeah. But in the yeah.
So I think you can start with a non-feasible project, but you pass it through your project.
But you have to be close to the manifold of the system. You can do it, for sure. Yeah. If you are far away and you project, you can get some trajectory that's something else. Yeah, exactly.
Yeah, there's a slide doing a loiter with wind when you go to this.
Yeah. This one or this one?
You're using like constant wind for the whole region.
Yeah, in this case, yes, yes.
And another question is,
This one? Ah.
so my question is, what's your cost function in that case? Can you say energy efficient?
Yeah, it's energy efficient. No, I was not considered exactly the fuel consumption, but I considered a very high weight on the you know on the control inputs. So we want to have a trajectory with the U, which is as small as possible. So we don't using high thrust or something else. Okay, which in some sense linked to the fuel consumption. Because also the roll is an input. So if you're rolling, yeah.
So last question, there's divided this constraint velocity and a graph. Do you understand what kind of
The beginning. Yeah, because it's not my contribution here. Yeah, this one, right? So here, for example, for the airspeed, you want to have some constraints on the airspeed has to be greater than the stall, the minimum airspeed, and the maximum one, probably. Okay. So in that case, you have some, some non-smooth function describing these constraints. In order to include this non-smooth function in our optimization framework, we can use this quadratic approximation. So here we are saying that C or the airspeed has to be less or equal to, it has to be negative in this case. Yeah. So we have to be here in this region. And actually, so yeah, I need to explain a little bit more about this barrier function.
So you have a smooth.
In this case, we have a smooth function enforce the constraint. This smooth function, this quadratic function, enforce this constraint. And what you can see is that when you update the parameter of your barrier function, this quadratic function becomes something like very high steep here, then constant and high here. So it approximates very well the initial constraint here.
So, is Pronto, I'm just curious, is it like open source, is it a commercial product?
No, not yet at least. So John, yeah, it's almost 10 years that we're working together. So yeah, so no, it's not. Yeah, we can ask. Yeah, sure. Yeah. Yeah, MATLAB. So that the integration of the dynamics in written, you can write it in C. Yeah. So to speed up the computation. The projection is also in C and so on.
But C inside MATLAB.
Inside, yeah. So you have a block, a Simulink block, which called a C function and so on. Yeah, S function, exactly.
When you are considering the wind loads, what's the maximum wind load you are taking in account for your solution?
The wind?
When you are taking the wind loads, the environmental disturbances, the winds in your simulation, when you are doing the
This one? Right. So in this case, it was like 1 meter per second for the wind, then 3 meters per second, and 5. Yeah. And then I tried to increase the magnitude of the wind, and it was not able to. You have to probably develop a new strategy to compute trajectories.
Have you considered range just as like
Yeah, constant. Constant, going this direction, you see? These arrows.
but different patterns? Have you tried to see it in different patterns like clockwise?
So if you want a space-varying wind, you can do it pretty. It's very straightforward, and it's actually what it is in this slide. But you see here, we have a space-varying wind, and actually this is tricky because here the wind is pushing the UAV away from the ground station. So the UAV has to compensate the wind and satisfy the communication constraint. So this is a ad hoc simulation, just to highlight this behavior. Yeah, so if you have a grid in space, just yeah. The important thing is that you have a smooth, as I said before, a smooth. I don't remember how I implemented this, but it's something like sine, cosine, something like that. So there is a map. So in a given position, you call this map, and you get the magnitude of the wind. Just. What? Yeah, kind of. Yeah, exactly. And this is actually what I use also for the decided path. Okay. So you have something 0 for the straight line. You have the sigmoid, and then increase, constant curvature, then decrease, and so on. Yeah.
And if you decrease, you will decrease lift and also
Yeah.
risk going below stall speed. Did you kind of take that into account, or?
So for the simple model, no.
Yeah,
But yeah, no. Every time you need a trade-off between complexity of the equation and dynamic features that you want to capture.
Yeah.
So.
It's quadratic from the lift. So
Yeah, understand. But for the 2D model like this one, I'm going to skip very fast. The 2 model with wind. This one, okay. Here, the drag depends on the airspeed, and in some sense, it takes into account the lift. Okay.
I was wondering if you could do the same with constant airspeed, or
I don't know.
if you, or
That's why you were asking. Yes. No, I don't know.
just constant airspeed and not with just the thrust. If you keep the thrust in a different controller.
Yeah, I understand.
Couple that somehow.
Yeah, to think about. Yeah. Maybe.
We may have discussed it before, but I don't remember discussion. So, with the use of projection operator and let's say some kind of complexity files, this may lead to sort of a discontinuous behavior. Generally speaking,
Okay.
and when shimmy is, I'm getting sort of guarantees, let's say the framework that
No, I mean guarantee or. Yeah, okay, so the point is that this is why I also add these slides on the UAV model. So when you want to do this exploration, trajectory exploration, you need to be like an expert of the dynamics of your UAV, okay? So when you set the desired path, the desired trajectory, you do this projection, somehow every step you have this projection, you need to know what's going on there. You can have something weird, but because mainly if you're using a complex model and you are using like a very simple trajectory to initialize the algorithm, you project it, you're far away. Oh, probably you are in the manifold for sure because you are project, but you are in some region of the manifold that is far away from the minimum. So you can have some weird behavior, but yeah. Thanks. Landing the UGV, the ground vehicle. There is wind over there, a static one. I don't know if there is. Yeah, there is a static time invariant wind. Actually, it was constant, yeah. So, of course, the wind was affecting. There is not. Yeah. But by the way, there is in the simulation, I didn't put the error, but there is simulation. Yeah. So the wind is affecting the UAV motion, but not the UGV.